carefully, what happens for the resistors? Is there some relationship between the resistors? We say they're in series and they're in parallel, in neither one.
They're all in parallel.
They're all in parallel, right? It's not as obvious because of the way that it's drawn, but they actually are in parallel, right? So for example, these guys connected here and here, but this is the same point as this one and the same point as this one, and then this is the same point as, let's see, as this one, right? And then the same point as this one. So they're all between these nodes and these nodes. So then they are in parallel, so I can actually combine all of them into a single parallel resistor. And so I'm going to have then my current source here, which is 2 amperes, then a parallel resistor, and I still have, let's see, and then I have the parallel resistor. And then when I have 3, it's a little bit different, but we can use the formula where we have 1 over 1 resistor. Ohm is the resistance. And then once I have the resistance, then it should be obvious how to get the voltage, right? Except that we have to be careful here about the polarity, because notice the way the polarity is there versus where the current is coming in. So to use Ohm's law, remember Ohm's law is the R times voltage is R times I, but I coming into the positive side. Right? Here I is coming into the negative side, right? So this current is coming into here. So it's coming into the negative side. So then in this particular case, then we have that so then the voltage is going to be equal to basically minus. I have to put a minus sign, so that basically I reverse the current, right? Minus 2 times Rp, which is equal to minus 1. So I have minus 1 volt. And there, it's important that when you do the simplification of the resistor, you keep in mind where the voltage stays relative to the current, right? Because here, if you notice this plus sign for the voltage is on the tail of the arrow there for the current. So that's important that we keep the same one there, because otherwise you change the definition of the, and you're going to get the wrong answer. So always make, when you do simplifications, always make sure that you keep things in the same labeling as you had before. But you see, these are very simple circuits now, right? It's not a huge node voltage thing when you have to do a lot of algebra. So this is a lot simpler. And if we do the third case, then let's look at the third case. So what I'm going to do then is I'm going to short the first one, and I'm going to disconnect the current source, and so you have the other one. And so I get the circuit there on the right, and again I want the voltage source there. Sorry, the voltage on the 2 ohm resistor, and so it's basically the same scenario as we had in the first case, right? Use a different voltage source, but now we have these 2 resistors are in parallel, so these guys connected here and here, same as these guys. So these 2 guys are in parallel, so I can combine them into a single parallel resistor. So my circuit now looks like Rp plus 1 volt minus here, but now Rp is actually exactly the same one as before. It's 2 times the 2 on 1 ohm parallel. So Rp is 2/3, and now again we have a single loop. The resistors are in series, 1 voltage source. I can divide the voltage. In this case, we had is going to be the voltage source, which is 1 times the resistor where I want the voltage, right? So times the 2 ohm divided by the 2 plus Rp. So I get the 2 divided by 2 plus 2/3. 6 3/4. So we get 3/4 volts for that one. And again, it's important when we do voltage division to realize that the polarities are in the correct direction, right? Otherwise, you might need a minus sign there. But here, the voltage division is going in the right direction. So again, it's a simple circuit that you end up with, right? It's something that's simple to solve. So that's the advantage of the superposition principle, that it allows you to reduce a circuit into multiple, yes, there's a lot of them, but usually simpler circuits that you can solve. Yes?
So what we do is we take all the V hats that we obtained in all three circuits, add them all up, and then that's the true voltage that passes through that resistor?
Exactly. So then the last step that we need is now we add all of them together. So now what we do is, so we take, so V hat, then we do the final solution, then V hat is going to be equal to the 1/2 which we got from the first part, minus the 1 from we got from the second part, plus the 3/4 that we got from the last one. And so we end up getting plus a quarter. So that's the fancy. At the end, you just add all of the individual components. So then that's the advantage of superposition, that you can do this separately and then combine everything in the end. Any questions about the general idea or the example in particular? Okay, so that's a superposition and linearity principle. Now these actually, we're going to use it then for the next part of the course. So let me bring up this. Well, let me raise this first. Okay, so what we're going to use this next is for something called Thevenin and Norton equivalence. And so what we do there is the following. So, okay, what we try to do in this chapter is analyze complex circuits, but we've seen that sometimes it's a good idea to simplify the calculation. So what we're going to do now is, suppose we have a very, can you guys actually see through the white there? Is that okay? Okay. So you have a complex, let me say resistor circuit. So it's a big circuit, you have a big board and it has a lot of stuff in it. And then you're going to have a terminal here A and a terminal here B, and you're going to connect it to something. And you want to see how this can be modeled so that you don't have to recalculate everything every time you connect something. So for example, you might want to connect a resistor here and then see what happens. Right? But then if I put a resistor there, do I have to analyze everything using, say, the node voltage method or any other way? Or can I set myself some time and just have a model for this that I can quickly adjust just for the resistor? And that's what Norton is going to do. What we're going to try to do is basically assume that we have some current. I'm going to use I. Some current coming out here, and assume we're going to have some voltage here. And so every time we connect something, then we're going to be able to represent this whole complex thing in terms of something that's a lot simpler to, especially for analysis. So what we're going to do then is we're going to turn this into something that's just a voltage source in series with a resistor. And we want basically the same current coming out, and we want the same voltage across this terminal. And we're going to call this voltage, because this VT for Thevenin voltage. And then this is going to be called RT for Thevenin's resistance. So the first question is, can I actually do this? Is it possible? And then the question after that is, how do I do that? So as for answering that, can I do this? Well, this is where it's important, at least at this point, to say that this is a resisted circuit. Because if we have a resisted circuit, and basically if I want to look at the voltage say here, so what do I now know based on the superposition principle? That if I look at this voltage, this is going to be a linear combination of all the independent sources here. Same thing with the current. So basically what this is going to turn out to be, and I'm not going to have time to go through this, probably see on Monday, basically this is going to be related to that term, to all the combination of the independent sources in here. And then this is going to be related to something else, and I'm sure you're going to see that on Monday, we're out of time. So I was using you guys.